We can.
Perfect. Let me just put it in. Okay. So my name's Romane. I'm in my final year in UL doing applied physics. This is my final year project that I'm working on with Dr. Tafal Saeed. He's actually the head of the physics department. It is about creating an application for calculating contrast in X-ray images. So that sounds a bit complicated, but it'll make sense further on. Just a brief overview. So I'll go through the background, the methods, the findings, the conclusions, future, and some acknowledgements. So I'll just change that to a laser pointer. The basis of the project is basically about minimally invasive procedures. So where you're having catheters, stents, or guide wires, for example, used in procedures, this is usually monitored by a CT using X-ray radiation. And obviously a key component of this is how visible those materials are during the procedure. So the project kind of seeks to create a user-friendly program that could be used by professionals to help material selection to optimize these procedures. So if you have a catheter or a stent, you can see it. You know before you do the procedure that this material is going to be very visible and easy to follow throughout in comparison to like the soft tissue in the bone that would also be seen by the CT. So just a bit of physics background. X-rays are ionizing radiation. They pass through your skin and your bone and essentially the whole body. They are generated by X-ray tubes, which you can see in this figure. They are produced through heating of the filament, which accelerates the electrons towards the tungsten target. And then when it strikes the target, there are two mechanisms that can create the X-rays. The braking radiation, which is energy produced through them decelerating when they come across the target, and characteristic radiation, which is when they knock an electron out of one of the shells, and then the energy used to fill the shell creates the characteristic radiation. So then on the graph below, you can see that the braking radiation is a continuous curve, and then the characteristic radiation is just seen as spikes, and it's characteristic because it changes for each element. And then there's two key formulas that I used to write the program. The first one here is the mass attenuation coefficient. So this is distinct for each element, but for my project, I wanted the linear attenuation coefficient. So that's just the mass attenuation coefficient is the linear one normalized by the density of whatever material you're using. So I'm actually working backwards and multiplying the mass by the density because generally the mass attenuation coefficients are what you would find in databases. Then the second formula is the actual contrast formula. So it looks very complicated, but essentially it's the difference in the original intensity of the X-ray beam minus the intensity after it passes through the material and divided again by the initial intensity. And here you can see that the transmitted intensity is the original multiplied by the exponential of the attenuation coefficient and d, which is the thickness of the material being used. So this is the flow of code that I used. Essentially, I chose the voltage. I started off with set parameters, so just one voltage, one material. So I chose, say, 100 kVp, imported this beam spectrum. So the beam spectrum is the initial intensity, basically. And then I imported the densities and the atomic numbers of materials. That's open source, so very easy to find. Then I imported the mass attenuation coefficient. They came from the NIST website, the National Institute of Standards and Technology. They are all in the form of the mass attenuation. So then I multiplied them by the densities that I had also imported, and that creates the linear attenuation coefficient. And then using the formula here, we calculate the transmission spectrum, and then the overall contrast value. Then after I had done that for a set, maybe magnesium and 100 kilovolts, I then worked on adjusting the voltage and the materials and things like that. So then this is the calculator to date. So I don't have a coding background, which is why I partially chose this project. So for anyone who's experienced in coding, it might look a bit basic, but you essentially choose your elements. You can either put one element and then just enter the fractional weight as one, or you can do a compound. And it's not just limited to elements. I actually have like soft tissue, water. There's various compounds actually in this drop-down box as well. The material thickness, the anode type, and the voltage of the tube, they can all be inputted, and then the calculate button will provide the contrast. You can also graph the linear attenuation and the X-ray spectrum. And then you have the option to save the input along with the contrast value as a CSV file in case you want to go back and look at it later. So these are just some of the results of the graphs. So I have a single element here, magnesium, that's the linear attenuation. The same here for calcium fluoride. Then the X-ray spectrum here, so you can see this one is for 100 kilovolts for a tungsten rhenium anode at 10 degrees with 2.5 millimeter aluminium filtration and a focal distance of 1 meter. So that's a lot of information, but that's just the tube setting. So you can have the X-ray tubes, they come in all sorts of forms. So I needed to have all those inputted into my program for it to be the most useful in a kind of hospital setting. Because, you know, for example, if you're doing a mammograph, that's a completely different type of tube. You'd be using a molybdenum anode, and the voltages are way lower. So I needed to include a broad range. So then this is the kind of preliminary validation that's been done. I was supplied this image by Alice Shannon. She is also a student at UL. She's a PhD student, I think. And the part of the image that I was interested in is this bit. This is an aluminium wedge going from 1 to 10 millimeters. So a fairly simple kind of thing that I could put into my program to test to see how accurate it was. So the orange line here is my program, and then the blue line is the contrast I got using ImageJ software, which basically picks the color. So, you know, the color in the background would be 0, and then the brightest color went to like 250, I think. So then that's just kind of a basic contrast calculation. But as you can see, they line up fairly well. So I was happy with that for a preliminary validation. So then some conclusions. It successfully creates compounds, graphs. That first validation that you just saw, we're fairly happy with it. It does demonstrate, the most important thing is that it demonstrates that it is possible to create a user-friendly application that could be offered to professionals, you know, either in the hospital, but even researchers who are working with compounds and they want to know how they react with an X-ray. There's always room for improvement, of course, increasing the options for the materials, for the tube, for everything basically. The more information you have, like the more accurate it is. Then some future developments. So I'm actually going to be working on this with the university for the summer until I start my master's. There's a lot of kind of technical stuff that needs to be done, but some of the things I look forward to is adding more, the option for more elements. So instead of just having a compound of 2 elements, I could work on having a compound of 3 or 4, or having an option where people can put as many as they want. Working on a phantom material, because at the moment it's just kind of the bare X-ray hitting a material, whereas in reality you're going to have a phantom, you're going to have a patient that the X-ray will also have to travel through. And then,
sorry to interrupt you, Romane, you've got 1 minute left there.
Yeah, perfect. And then to make it into it, right now it's just a DOI that I have kind of as an executable, but to make it into an actual online application where people could just, you know, look up the website and then they have it there. And then just some acknowledgements. I want to thank my supervisor, Dr. Chafal Saeed, Charlie O'Mahony, his PhD student who's helped me a lot, Alice Shannon for to find the image, and friends and family for advice during the whole process. Yeah, and then that's it if there's any questions.
Thank you so much, Romane. That was incredible. I'm just going to stop the recording there for the questions.
Yeah.